Okay, we are officially recording now. And before we hop back onto that Jupyter Notebook, I just wanted to address Felix's question from yesterday about that map quality score. And he had asked why the map quality score wouldn't be available. So 255 indicates mapping is not available. So 255 is actually the highest value that you can get for mapping quality based on what samtools allows. And so this mapping quality, the better your quality, the higher your score, and the worse your quality, the lower your score. And that 255 value is actually specific to STAR. It's also specific to some other alignment tools. So the way that the mapping quality score is calculated is actually going to be unique to each specific alignment tool that you use. So depending on the alignment tool you use, you'll get a different mapping quality score. And as I was kind of reminding myself of this stuff last night and looking things up, I found quite a bit of forums with some angry bioinformaticians about this not being streamlined and consistent for all alignment platforms. So make sure if you guys are ever looking at a couple different experiments or different studies that you know how they did their alignment before you make any conclusions based on the mapping quality. So, and if you go to the STAR manual, what you'll see in what I did is this is that large STAR manual. I'll show you guys where that link is again in the Jupyter Notebook when we get to that. But I just went on the STAR manual and I basically just searched for map quality, and it gives a definition of how they calculate their map quality for that STAR alignment tool. And so the mapping quality, they give a value, they just give the highest value possible that samtools allows for uniquely mapped reads. So it's not that the mapping quality is unavailable, it's just that there's no other places that those uniquely mapped reads aligns to, and so it's going to be really the best mapping quality. So that's where the 255 comes from. It means that the reads were uniquely mapped. They haven't been mapped anywhere else on the genome. And then for reads that have been mapped to multiple locations on the genome, STAR calculates the mapping quality using this equation here. So they take -10 times log base 10 of 1 minus 1 divided by the nmap. And the nmap is the number of loci that the read aligns to. So how many different places on the genome the reads align to will be that nmap number. And that's represented in that NH flag. So if you guys can recall from the lecture here, those additional columns from 12 plus on, those are going to be the SAM flags. And you can set as many or as few of those as you want using the option outsam attributes of the STAR command. And so some of it of course, like most of the options in STAR has default values, and one of those default values is that NH SAM flag. And so we'll take a look at what that is in the alignments that we did yesterday, and you can see how that mapping quality is going to be calculated. So with that, I want everyone to go ahead and hop to their Jupyter Hub and make sure you guys can open up your FastQ Accounts Jupyter Notebook if you don't already have it up. And I'll give you a minute or two to do that. And while you guys are doing that, I did just want to remind you all that I did open up I did upload yesterday's materials to the Google Drive. So you'll see a Day4 folder now in that main folder. And you'll see the lecture up to what we covered yesterday. And then if you go to the recordings, you'll see all the recordings. So it's broken up into 4 parts in there. So you guys can go ahead and review that as you see fit. I didn't put any of the answer keys on there because I'll put the full answer key to the Jupyter Notebook tomorrow. Are we still going to be able to access it after the boot camp? Yeah, I was actually gonna bring this up tomorrow, but we could bring it up now since we have Steve Boring on the call. So Steve, would it be possible to have the participants have access to the compute cluster for, say, another week or two after the course? Stephen, if you're talking,
Yeah.
your mic is muted.
Yes. I was going to say for the San Jose State students, they can have access to from until they graduate, basically. But I guess we could do like we did for the trial. Give you, I could give you an extra week for the
Great.
people for the people that aren't San Jose State students.
Okay, that sounds great. Thank you so much, Stephen. So yeah, for those of you who aren't San Jose State students, you'll have access for at least another week. And so you'll be able to go ahead and walk yourselves through all the notebooks all over again. I actually highly recommend that. While it's fresh in your mind, just doing it once more can really solidify some of these concepts and how we run some things. And you guys will have all the recordings so you can kind of follow along again. And at the end of tomorrow's Jupyter Notebook, I'll have Lauren show you guys all how to refresh your Jupyter Notebooks so that way you can remove all the outputs and be able to run them all again. Okay. Is there anyone who doesn't have their RNA-seq FastQ accounts Jupyter Notebooks up? Okay, awesome. Let's get going then. If you guys can remember from the Unix lecture, when you guys set a variable, that variable is only maintained for the instance that you're on. So as soon as you log off, you lose all your variables. And so I want everyone to scroll up to the top of the Jupyter Notebook. And you guys can go to where it says define paths to the process data. And I want everyone to rerun this code block. So this is going to reset our variables that indicate the location on the cluster of where all the data that we're using is stored. Was there anyone who wasn't able to do that? Oh, and I guess I do want to make sure too, can everyone look down here on their Jupyter Notebook and make sure that they have the Python 3 idle? And if you don't, put a message in the chat. Okay. And while we're up here, now we have our variables defined, just to remind you guys kind of where we are in the pipeline. So yesterday we took a look at the quality of our raw reads. Based on that quality check, we went ahead and we trimmed and filtered our raw data using a Trim Galore tool, which uses cut adapt underneath the hood. And then we took a look at the quality of our trim data and saw that indeed our quality was improved, and we were able to remove all of the adapters that we saw from our raw data. And then towards the end of the day yesterday, I showed you guys how I created a star index, but of course that only needs to be done one time as long as you're analyzing data with the same reference genome and the same read length. So since we're all analyzing the same data, you guys were all able to utilize the star index that I had created when preparing for the bootcamp. And then we ended yesterday by aligning our trimmed reads to our mouse star index, so ultimately to the reference genome, and ended by taking a look at that. So we'll start there, and so we can remind ourselves of how that alignment went and also take a look at those mapping qualities. And then we're going to go ahead and compile that aligned data and take a look at how the alignment went for all the samples. So you guys now go ahead and scroll all the way down right to where we left off yesterday. So we left off taking a look at the aligned to transcriptome BAM file, which is one of two BAM files that are outputted from the GeneLab standard pipeline using STAR. And so just to kind of remind you guys all, so this is at step 4A. You also could have gotten there by clicking on the index at the top of the notebook too. Should bring you right to this spot. And table of contents, that was what I was looking for. And so just to remind you guys, we used all these options for STAR, and any options that aren't listed here, we just use the default options. And so just to point out this quant mode here, this option, where we put the option transcriptome SAM. So that tells it to also output an alignment for the transcriptome. So that's another cool feature of STAR, that you can generate both alignment to the genome as well as alignment to the transcriptome. And then the option right above it is out SAM type, and we set it to output as a BAM file. So you could also output as a SAM file. And SAM is the sequence alignment map, and BAM is a binary alignment map. So it's really just a compressed version of the SAM file. And we asked it to sort our alignment files based on the coordinates, so based on the genomic coordinates. And so that's why we had it in aligned, sorted by coordinate BAM file. So that one's going to be aligned to the genome. And then it also, thanks to this option, output it aligned to transcriptome BAM file. And that's the file that we're going to be feeding into our counts tool. And so that's why that's the one that we took a look at yesterday. And again, I have definitions for all of those options here. So I guess I'll open this up now. If any of you guys took a look at definitions of all of these options, I just want to give you guys an opportunity to ask questions about any of the definitions. It might not make sense to you. It's okay if you hadn't had a chance to read through all of them yet. I know we've been going over a lot. Okay, if you do happen to read up on these definitions, and if you have any questions, please feel free to go ahead and ask me. And so in addition to our BAM files, we also have several other output datas. Overhang. So the align SJB min overhang, so just both of these overhangs. So this is going to be looking at the minimum overhang for the unannotated splice alignments and also for annotated splice alignments. And so if you guys can remember, for STAR, we do a 2-pass alignment. So we'll do our first pass based on the index that we generated from the FASTA file and the respective GTF file that we gave it. And then what STAR will do is, after it goes through and runs that alignment through the first time, it will then go back, or as it goes through and does the alignment, if it identifies any splice junctions that weren't in the original annotation file that you gave it, it'll save those, it'll add it back onto the index, and then you can do another round of alignment, and it'll use that updated index, so that way you can detect those novel splice junctions. And so those are going to be some of the unannotated, those would be the unannotated splice junctions there. And so it's asking you if, when you are looking for those splice junctions, how much past that splice junction are you going to make it the minimum to look for that. And so the values that we have for those are going to be, for our annotated splice junction, we give that a value of 8. So that's 8 nucleotides that it's gonna allow for that overhang. And then for the new or the unannotated splice junctions, we're a little bit more stringent on those. So we give that an overhang minimum of 1. Or sorry, less stringent, with an overhang minimum of 1, because we want to allow us to be able to identify the ones that weren't in our annotation. Does that help? And then, of course, I did promise you guys I'd show you this. So you guys can go to the GTF files, my STAR. That's ensemble database. You guys can go, I think it's right here. Yeah, so you guys can go to the splice aligner here. So this will give you, this is the tool. And then in the README of the tool, you can grab the manual here. And then in this manual, you can also download this and save it as a PDF, which is what I did here, just to make searching easier. And so we can look up more information on any of the options as well. So I'll go ahead and copy that option and just show you how I take a look at these anytime I need to be reminded of what this stuff means. So again, this is the minimum overhang for splice alignments. So it's how far from the read to the when it's doing the alignment that it allows kind of wiggle room of that splice junction location. Lauren, do you have a different way of saying that?
No, I think that's pretty good. Let me see if I can find another explanation online.
Take the whiteboard out. Not sure if I could explain this with the whiteboard. So yeah, so I'll put some stuff. I don't want it to take time now on the whiteboard, but during the break, I will set up a whiteboard with some pictorial representation of this overhang. So, and then we'll start next time. We'll start after the break with going over that overhang and how it's calculated. So hold on to it, and I'll give you a pictorial representation during the break of that. Okay. Any other questions about any of these options here, for those of you guys who read the definition? Also, why do we align to the transcriptome? So for differential gene expression, we're looking at annotated genes because we need to know which genes we have in order to know if they're differentially expressed. And so we're looking at specifically the transcriptome of our annotated genes to perform the differential gene expression, and the RSEM tool, which is what we use to do our quantitation, takes in the align to transcriptome file. So there are some tools that do counting that will look at the align to coordinates, but they'll also have to figure out which ones were transcripts of those genomics coordinates, right, to be able to do the differential gene expression, especially if you're identifying splice isoforms. So genes can have multiple transcripts, and so multiple transcripts, each transcript being a different splice isoform. And so to get more information too from that differential gene expression, we use the align to transcriptome mapped file. Does that make sense? Awesome. Okay. If you guys have any other questions about any options, go ahead and put those in the chat. And as I see them, I will address them as best I can. And anything that I can't address adequately, I'll get to over the break and get back to you guys. Okay, so if you remember, we took a look at the standard output after our alignment. And one nice thing about the standard output is it will tell you if it finishes successfully, and it kind of tells you each step along the way of the process. We noticed that it took a long time, but of course, as I mentioned last time, it's because I was running this on one core originally when I had set this up, and your guys' jobs, I had changed, per Steven's suggestion, the NTAS option in the Slurm command, which allowed it to run over 4 cores, and actually all of your guys' jobs, I just checked the cluster this morning, have completed, which is nice. So we answered some of these questions yesterday. I just want to do a quick reminder of the align to transcriptome out BAM file, and we piped this into head. So as a reminder, the BAM file is a compressed file, so it's a compressed form of SAM. And so in order to view it, we have to uncompress it, and samtools is a tool that allows us to have this view option, and that enables uncompression of BAM files into SAM files, so that way we could take a look at them. And I just piped it into head because, remember, this is aligning all of our reads, and there's over 60 million reads, as we saw earlier in this sample. And so we really just want to look at the first few here. And then you got the questions here at the bottom that we went over, taking a look at that BAM file. And as we took a look yesterday, we noticed that there are 5 unique transcripts based on the unique transcript IDs in column 3 here. And then we took a look at how many reads were represented. And as Felix astutely pointed out, that there's actually only 2 read pairs represented, as you can see by the sequence of one of the mates of the mate pair here, the other mate of the mate pair here, and then you see those same sequences duplicated for the next transcript, which means that they align to both. And then if you look at the flag here, the SAM flag, going to the decoder, which is what we did yesterday, we were able to see that based on, even though this is the same mate pair here, aligning to this transcriptome ending in 277, or this transcript ending in 277, and also aligning to the transcript ending in 2409, we see that if you take a look at the code, it will tell you. So this one, it doesn't tell you, it doesn't have that not primary alignment clicked, so you can assume that this is where it aligned to first, or where it found that first alignment, or where it aligns to best. And then if you look at the next, so that again, this is the same read, just where it aligns to on the other location that it maps to. And so taking a look at that flag, that 419 flag here, using this decoder brought to you by the Broad Institute, we can now see that this not primary alignment is selected. And so we know that that's kind of the secondary alignment. And again, those are determined based on how many base pairs of the read align to the reference. And so the more base pairs that align, the more likely it is to be the primary alignment. However, if it aligns exactly to multiple locations, then I'm pretty sure which one is the primary is determined based on where it aligns to first. And then so, as you notice, again, taking a look at these sequences, and as Felix pointed out yesterday, that we see another mate pair here. So you'll notice that this sequence is different from the 2 sequences in the above transcripts. And then this is its mate pair coming right after it here. And then we see those same mate pairs repeated for the last 2 transcripts as well. And so this mate pair is actually aligning to 3 locations on the 3 locations on the genome. Or sorry, on the transcriptome, because this is the aligned to transcriptome file. And so now let's take a look at this mapping quality score, which is this column here. So again, the mapping quality is going to be your 5th column of your aligned to transcriptome, or of your aligned to transcriptome or aligned to genome BAM file. And so looking at that mapping score, if you guys remember what I just talked about this morning, is that that's determined based on the number of locations that the read pairs align to. And so if this read pair were to align uniquely, it'll give the max score possible of the mapping quality, which is 255. If it doesn't align uniquely, then that mapping score is based on the number of locations that it maps to. And so for this first mate pair here, and the SAM flag that indicates how many places the reads align to is going to be represented by this NH flag. And so we'll have, it's the syntax of this is NH : I : and then this is going to be the number of locations that the read aligns to. So we can see, we could have looked here, sorry I didn't mention this yesterday, then we can see that this particular read aligns to 2 locations on the genome, and we see that those locations are on this transcriptome and then also this transcriptome. And then we use that value to calculate this mapping quality score. And again, you find out how that's calculated by looking at the alignment tool that you use. And so we use the alignment tool of star. We know that this aligned to 2 locations. So if you go over here to star, this is the star manual again, and you could just do Control F and take a look for map Q. And you could do this for most of the alignments, but another thing that I was finding yesterday is a lot of the bioinformaticians were also upset because how the mapping quality score is calculated is not necessarily apparent in the documentation for all the tools. Luckily, STAR is fairly well documented, and so they do tell us how they calculate their mapping quality score. And so again, that's going to be -10 times the log of 1 minus 1 over the number of places that the read maps. And so we saw in that first mate pair that we see in our aligned to transcriptome BAM file that it maps to 2 locations. So then this would be 1 divided by 2 is of course 0.5. 1 minus 0.5 is going to be 0.5. The log 10 of 0.5, which I calculated yesterday, is going to be a negative 0.30 and then a bunch of numbers after it. And so you take that negative 0.30 bunch of numbers and multiply it by 10. So basically move that decimal place one over to the right. And that log value is negative because you're taking the log of a fraction. And so that's why you're multiplying this by -10 to give you a positive value. So that negative 0.30, which is the log base 10 of 0.5, is going to be negative 0.30 times -10 is going to make that a positive value, and you move that decimal place over one to the right. So that gives you a value of 3.0 something. And then this INT says that it takes the integer of that value. And so that is how this value of 3 was calculated for the mapping quality of this particular read and also its read mate. And so for the next set of read pairs that we see mapping to 3 locations, at least looking at this view, how many locations is it actually mapping to? So for the next set of read pairs, so here and here, how many locations on the genome are those reads mapping to? Should be able to find it with that NH, yeah. So Christina Zinrua is saying 1, so why do you guys think 1? I think you're probably just looking at the wrong SAM flag. So it's gonna be indicated by that NH SAM flag. Yeah, I figured. So the number of places that it maps to is gonna be indicated by this NHI flag. So you'll notice here that it's actually 5. And so Diksha, you were right. So it's 5 for the next set of reads. And so we're actually only seeing 3 of those 5 locations looking at the first 10 lines of this aligned to transcriptome file. So I can bet that if we take a look at the next 4 lines, which will represent the next mapping of the next 4 reads. So we do read, it goes, read pairs usually come after each other because we sorted this. It's another reason why we sort. It's because a lot of tools want to see the mate pairs coming right after each other in the BAM file. So one way to do that is by sorting them. So that's why we add that option here. And so I bet if we add an extra 4 lines to this head function here, that we'll see that same mate pair, and we could see the other 2 transcripts that it's mapped to. So let's go ahead and try that. Does anybody remember the flag for head that we give when we want to print more than the default 10 lines in Unix? Yeah, Diksha, add -n for sure. Yeah. So -n space, and then we want to add 4 lines to the default of 10. So what value should we put here? 14. Yeah, A1, that's right. So guys, go ahead and run that, and let's see if we indeed see those same mate pairs. And so we do. So now in kind of one easy way that this isn't always true because sometimes the insert size is going to be the same for different read pairs. But one quick way to do this is you'll notice that these first two, or I should say first two transcripts indicated, first 4 reads, 2 mate pairs. We see that 167 insert size, again, in one direction, which is, so I guess I should ask you guys, this first one as a reminder, this value here, which is the insert size, I already told you that. But the value here, what does that indicate? So if this is positive, what does that mean? It has to do with the orientation relative to the reference strand. Yeah, that's right. When it has to do with the reference strand, is positive indicate the same or the opposite orientation? Same. Yeah. So a positive value here is going to indicate that this is in the same orientation as the reference. And a negative is, of course, going to be the reverse orientation of the reference. And so we see that this mate pair is 167, the total insert size, and then it's that same mate pair just aligning somewhere different, so still that 167 size. And so we can see here that that next mate pair that maps to 5 different locations on the genome, represented by the 5 transcripts, is 203. So we see 203, and then this is that one transcript that we saw before, 203 again here for the aligning to the same strand, aligning to the opposite strand of the reference. Is we see this next transcript here, and then we see the 3rd transcript that it aligned to, and then these are the 4 new lines that we just looked at by adding that -n function, or that -n option to the head function. And we can see that indeed, if you take a look at, so let's start here. So in the positive direction, we see that's what that sequence looks like. And then indeed, this is the same sequence in that first new line. And then its mate pair as well here. We see it, and its mate pair again comes after the next transcript that it's aligned to. And then we see that repeated one more time. And so we do see now all 5 transcripts that this mate pair is aligning to. And I just want to point out, because I know yesterday I did in my example when I was showing you guys multi-mapping, I used the example of 150 read length, or 150 base pairs as my example, and kind of Felix pointed out that was pretty surprising that long was, that repeat of that length could be seen in multiple locations in the genome. And as we're seeing in our actual data, that this is even longer, right? So this is 203 base pairs that are mapping to 5 different locations on the genome. So our genomes are highly repetitive. And that's, again, why longer reads are always going to be better. And so this is 5. Do you guys want to do 2 more lines to see if indeed the next transcript shown is one that a different set of reads aligned to? Yeah, let's do it. So if we want to see another 2 lines, what would we add to this number? Yeah, so this number would be 16, and we'll take a look at 2 additional lines. So go ahead and add 16 and run it. Then let's take a look at this next mate pair, and already we can see just by the insert length, we have a different insert length, which is going to be a pretty good indication that we have different read pair. And then just to check here, so looking at that sequence now compared to this sequence, and then of course look at the whole sequence, it's kind of cumbersome. So I really just take a look at the first few base pairs, and usually they're different within the first few base pairs. So this one starts GTC, and then this next one here that we see starts GTAA. So indeed, that's a different read. And so now we're seeing a different place. How do we know it's mapping to different parts of the genome and not the same part of genome, but just different transcripts? So you're saying the splice isoform, so the same gene, but we're looking at a splice isoform. Is that what you're asking? Yeah, good question. So we can actually take a look at the gene that this read is aligned to using the looking at the aligned to genome outBAM file, right? Because again, you're absolutely right. We can have multiple transcripts due to alternate splicing of our pre-mRNA to give us our mature mRNA, right? Which could be where this stuff was derived from. So one way to do this, I guess let's let's go ahead and see, right? So let's take that one of those reads. You can pick one. I'll take the one that's mapping to the same orientation of the reference, relative to the reference. And I think I could just do a Command C here and copy that sequence. There's probably other ways to do this, but you can also look up the transcript too in the GTF file. So the GTF file for that gene, so we can do this a couple ways. Let's take a look here, though. I think this way will also show if it's mapping a different gene. So I'm just going to copy this full sequence. And then let's add a code block. And I'm going to do the end of my script first just because I copied that and I want to copy something else. So end it with a pipe. And then just put that there for now. And then if you guys want to easily get to the start of your command, so you see how my cursor here is at the end? If you want to easily get to the start, you could do Control A, and it'll bring your cursor right to the start. Of course, we're in a Jupyter Notebook, so I guess you can just click there. And so now let's take a look, and instead of the align to transcriptome BAM file, we're going to take a look at the align sorted by coordinate file, which is the one to the genome. And so the end of that is this. And if you guys want to copy this, if you double click on that block that has the word in it, you'll be able to copy the text there. And then just when you're done copying it, press play, and you'll get it to look pretty again. And then we're just going to add that suffix to there, and then make sure you have your space. So now we're doing samtools view. So using samtools again to open up this time, we're going to open up that same sample, so that flight rep 1. Except now, instead of opening up the align to transcriptome BAM file, we're going to open up the align sorted by coordinate, which is the one that's aligned to the genome. And then we're going to pipe this into a function we haven't talked about yet, but this is another really useful function that I use all the time in Unix. It's called grep. And that allows you to pull out a string from your file, and you can see, and not only will it pull out your string, it'll pull out the full line of where your string came from. And you want to put what you're grepping in quotes. So you start with an open quote, and either single or double quotes will work for grep. I'm using single quotes. Make sure you put a quote both at the start, at the end. And again, this sequence is that read that mapped to the 5 different locations on the transcriptome. So right now we're taking a look and trying to pull out where that read maps to, this time looking at the genome mapping file. So that same read, again, we're looking to see where it's mapping to on the genome using this grep function. So this is going to open up that align to genome SAM file, BAM file. And then once we open it up, we're going to look for that whole sequence to see where it is in that file. So you guys can go ahead and run this. I haven't done this yet, so I'm not sure how long it'll take on the server. So it's going to go through line by line and search for that string.
Which sequence did you take?
Oh, good question. So I took this sequence here. So again, anywhere where it says 203 positive, the sequence that comes right after that. So remember, this map, the same exact sequence is the one that's mapping to 5 locations, or to 5 transcripts. And so yeah, again, I'm not sure how long this is going to take to run. And another thing we could do as well, which again would be using a grep file, but it actually will be going through fewer lines. So this is currently searching through all the lines in that BAM file, which again is like 60 million lines. Oh yeah, of course, good idea. So I copied and pasted that command in the chat. So you guys can just grab it from there. Kind of another thing we could do, which I probably should have done first, because it would have been faster, but it wouldn't have given us as much information, is another thing you can do is you can take a look at your GTF file. So that annotation file that you provided STAR to build the reference, and you can grep for one of these transcripts and see what genome it's associated with. So I'm not going to have you guys run that right now, just because we're all currently running this grep function here. But in the meantime, while we're waiting for that to run, any questions about calculating the mapping quality, or any other questions just about the format of this SAM file? Okay. A little nervous. Look at it saying busy. You see down here, Python 3 is busy. This star here, just as a reminder in Jupyter Notebooks, if it's a star and it doesn't have a number yet, that means it's currently running. Okay, mine finished running, but I don't see an output. Did anybody else get an output? It's done. So MapQ, yeah. So a MapQ 255 means that it's uniquely mapped, and because it's uniquely mapped, it doesn't have like a mapping quality based on how many places it maps to. So I think that's what the definition, I pulled that definition from the document for the SAM file. Yeah, not sure why that didn't work. Lauren, do you know why that didn't work? I feel like that should have worked.
That's a little mysterious to me too.
Right? That's frustrating.
Try again. More time.
I mean, I guess we could try again. I'm gonna go to the command line and see if I can't get it from there. I just want to get the path to. I guess I could have echoed it.
You could first see if samtools alone is working. And then if that gives you any output at all, see if maybe it's the grep that's taking too long.
Yeah.
Well, we know that samtools is working because we just ran those commands above it, right?
Yeah, it could just be that the grep is, it has to search through such a huge file.
We just reran this. So I guess let's try looking at that transcript. Did anyone get something? Is it because we didn't head it? Well, good question for sure. Because I was grepping for that one specific sequence, it should only give me the lines that contain that one sequence. And so since we know that it maps to 5 transcripts, if those transcripts each came from a unique gene, then the most lines we would get would be 5, representing the 5 unique genes where that transcript came from. So that's why I didn't include a head there, because the most lines we should have gotten would have been 5. So let's see if we can't grep from the GTF. If we can't grep from the GTF file. So let's go back down. We're going to add another code block. So let's go ahead and add another code block below this. And let's try, first let's list what's in this variable. And so again, we do the exclamation point because we're in Python and we're telling it that we want to run a Unix command. We want to run the Unix command ls, which you guys should all be familiar with now because of the Unix intro notebooks. And then we're looking at what is in this path. And that path is the location of where I have the GTF and the FASTA files that we use to generate the star index. And so now I want to add another block, and I want to cat, again, that same path, except this time I want to specifically look at this GTF file. And before we search for anything, let's just make sure that we can open this up. So let's put it into head. Are you guys seeing the start of that GTF file? Is there anyone who isn't seeing the beginning of the GTF file when they run this command here? And I'll paste this in the chat too. So if you guys are indeed, I think no one said anything, so hopefully you guys are all able to take a look at that. And so let's see if we can't run the grep command on this. So this cat file is going to have, or this file here is going to have fewer lines. And just to kind of show you how many lines, sorry guys, we're playing now, but these are kind of like things that I do often. So it's good to know. So if we cat this, we can also pipe this into a function we didn't go over in the Unix intro called WC. I believe that stands for word count. And we can tell it, instead of counting words, to count the number of lines with a -L option. And so if you guys now, instead of putting that head in there, go ahead and do the WC-L, and I'll put that in the chat again, and then run that. So what that's going to do is it's going to open up your GTF file, and then it's going to count how many lines there are, and it's going to give you a count of how many lines there are. So as you can see here, how many lines roughly are in this GTF file. You can go ahead and put your answer in the chat. Yeah, roughly 2 million. And so that's going to be way less than the 60 million we were trying to sort through above. But this, of course, doesn't contain any read information. So what we would have to search for here is one of those transcript names. And so that's why this one maybe would kind of takes a little longer, because we'd have to like look for each transcript. But if they're all there in the same gene, we would see it. So now I want you guys to go ahead and copy the name of the first gene that mate pair aligns to. So the gene, or the first transcript, excuse me, that mate pair aligns to. So the transcript ending in 7038. Go ahead and copy that, and I'll paste this command in the chat again too. And we're going to pipe that into the grep function again and see if this will work, because we're parsing through much fewer lines now. Line completing anything before the LS genome. Oh, yours hasn't finished, the LS. Christina, what command did you? You might say that again. It just finished. Okay, great. So now we're seeing here that, so this is another thing I should tell you guys. So in the GTF file, you actually might see the same gene being shown multiple times. Can't remember why that is off the top of my head. I think it's because of where the annotations were pulled from or originally made, or if new annotations were made for that same gene. I think it's just added on to the GTF file. Lauren, do you know that answer of why we're seeing this multiple lines for the same gene?
Yeah, I'm trying to see if there's a difference between the lines. It probably has to do with what you said about updated versions and stuff.
Yeah, so it looks like each line might have a different version. And so let's see if we have one.
Okay, so Felix is saying it looks like they're different isoforms.
Yeah, so we see that. Yeah, I think you're right, Felix. It is looking like that. So this particular gene is on chromosome 3, right? We know that from this first line here. And then it looks like there is a different line for each isoform. So Felix, you're absolutely right. And then you see in the transcript ID, so right next to transcript ID, we see the transcript that was pulled out using grep. And then we also see that it's that same transcript ID that's repeated. Yeah, so what I was hoping for is that it would have multiple transcripts ID for the same gene, but it's looking like we're only pulling out that one transcript for that gene. And these are all version 5. Yeah, I don't see any of the other transcripts. Does anyone else? So unfortunately, it's not listing. So one thing that we can do is, okay, now we know that this transcript comes from this gene that ends in 38170. And so we can kind of like make a note of that. I'll write it down. 38170 is where this first transcript comes from, what gene it comes from. And then we could basically run this again for each one of those 5 transcripts that mate pair is aligning to. So this was the first one that we looked at. So now we can go ahead and grab the next one and see if it's indeed that same gene, again, ending in 38170. Christina says, I can't get the cat, Gina. Oh, just got it. Perfect. Yeah, sometimes it takes a little bit, especially because we're all running the same thing here. So this is looking at that next transcript. And again, when we do this, we're going to look to see if it's the same gene ID. So go ahead and press play. And indeed it is. So now we're looking at that next transcript. So Felix, so far your hypothesis is looking right. And so this again is that same gene ID that ends in 38170 that tells me that this transcript is that this is a splice isoform of the same gene. So that's the second one. So let's see if that's true for the third one. 1, 2. I know they're spending time on this, but this is kind of the fun part, is taking a look and really diving into what your data is telling you. So you can go ahead and do it for that third one and run it again. And again, we see that it comes from gene ID that ends in 38170. So now we have, that's the third splice isoform. And so let's take a look at the last 2 here. This one, this is the next one. And so you see I'm just going down the line for each one of those 5 transcript IDs and pulling them out of the GTF file with this grep function and looking for what gene that transcript was originated from. So playing this again and again, we see now that that's the 4th transcript that's coming from that same gene ID ending in 38170. And then let's check that 5th one, just for completeness sake. And indeed, Felix, your hypothesis was absolutely right. So all 3 of those transcripts are all 5 of those transcripts are splice isoforms of each other, all derived from the same gene, 381, that ends in 38170 in terms of the ensemble ID. So yeah, great hypothesis, and it was right. Questions about what we just did and why we did it? Cool. You guys also got to learn some more Unix functions that are used pretty often in bioinformatics for doing exactly this sort of thing, right? For trying to figure out what's going on with your data, what's happening, where things are aligning to, and trying to make sense of it. So thank you for the question, Felix. Okay, and you can see, yeah, a ton of repeats. So this is one thing. So this is another thing I want you guys to make like a mental note of. So if you notice on the GTF file, we have several lines on the GTF file that are representative of the same gene and of the same transcript of that gene, right? So we have duplicates here. And so we will be sorting through and making sure that we remove any duplicates that's due to having duplicates in the GTF file. That's part of the filtering step that Lauren's going to go through with you guys. And then another way, just as a reminder, if you guys don't want to have all of this mess of information here, you can always come up to the top and just add a hashtag, which tells Unix that this is a comment and to ignore it and run it, and you'll get rid of that whole, oh, I just got rid of it. And I'll show you up here. So yeah, any of these things you could do that, and then you could just press play and it'll get rid of that output. Just to clarify, we changed from head to WC count and then to line count to better access the data. Can you say we modified that code? This was all different ways of looking at the same file. And so we were looking at different aspects of the file. So this cat command was always used, and that cat command was used that it opens up and it reads that GTF file. But because we didn't want to have like almost 2 million lines of the GTF file, we didn't want to see that. We first wanted to know how many lines were in there. And the reason I wanted to know that is because I wanted to know if it'll speed up that being able to do the grep, because grep will look through each line. So the more lines you have, the longer grep will take, which is, I think, the issue we were running into trying to use grep on the BAM file, because the BAM file adds over 60 million reads. And so I wanted to see if the GTF file first made sure and showed to all you guys that the GTF file does indeed have fewer lines. And so that's why I opened up the GTF file with cat and then piped it into this function called WC, which is word count, but you can give it an option -L, and instead of counting the number of words in the file, it'll count the number of lines. So that was why we did the WC-L. And then now that we were able to confirm that indeed it does have significantly fewer lines than the BAM file, so then I felt comfortable saying, okay, let's try now pulling out those transcripts from this GTF file instead, and using that way to see if indeed those transcripts all came from the same gene. And so then in the subsequent commands, what we did was, again, open up that file, except this time we piped the result of that. So the contents of that file were given to the function grep, and we told grep to search specifically for those transcripts, looking at one at a time. Does that answer your question, Eowyn? Awesome. Okay, good questions, guys. I'm glad we got to play around a little bit. Any other questions about the BAM file, the setup of the BAM file, mapping quality, multi-mapping, with the exception of how you count it, because we're going to do that in the lecture after we do alignment? So should all NH11 have, yes. Yeah, so if it only maps to one location, it should always have a quality of 255. Yeah, so Felix made a good point there. So remember this NH flag here. This NH flag here indicates the number of locations that the read maps to. So if it's a 1, that means that it's uniquely mapped, and based on how STAR calculates map quality, if it's uniquely mapped, it'll just give you the maximum map quality, which is 255. So it's not technically calculating anything there. So that's why it says that it can't be calculated, when in reality it means that it's really the best score that you can get. Good point, Felix. Other questions? I just want to make sure I check when I promised you guys a break. 10:40, cool, got a little time. Okay, let's move on then. So one of the other outputs that is useful, super useful in the alignment we went over in the lecture, and so that's the log final out file, and that one is going to give us information about how the mapping went. So what we're going to do here is we're first going to take a look at the log final out file for that same sample, that flight rep 1 sample that we just took a look at the mapping for. So you guys can go ahead and run that code block. And this file, the output of this should look familiar to you guys. You guys remember going over this in the lecture yesterday, and I noted some interesting things to point out. Before we answer the questions, just to make this less ambiguous, can you guys change this last one instead of unannotated? Change it to how many non-canonical. And we'll talk about what that means in a minute. So change where it says unannotated to non-canonical. It'll decrease confusion with that question. Okay, so now I want you guys to take a look at this log final out file, and we're going to answer some questions. And so I have my questions pulled up in a separate file, so that way I can leave this up for you guys to take a look at. So the first question I have for you guys is how many reads map to a unique location on the reference genome? And you could put this as either % or the full number or both. Okay, Diksha, you're so fast. Yeah. So Diksha, Kyle, Eowyn, Leah, all right. So we find that here. So the uniquely mapped number of reads, it'll give it in the actual number, as you guys all pointed out. So this is just over 52 million reads mapped uniquely, which is good. And looking at the overall percent, 77%, that's pretty good. So 77% of all of our reads map to a unique location on the genome. Next question I have for you guys is how many reads map to multiple locations on the genome? 11.77%. Yeah, Niksha, Eowyn, yes. All right. So that you find here. So again, it gives you the raw number of reads that map to multiple locations. So we achieved just over 8 million reads mapped to multiple locations on the genome. And you could see the percent breakdown of the total reads as, Leah, Emily, right, as 11.77%. So 11.77% of the reads are mapped to more than one location. So we have to figure out how to count those, or if we can count those. Next question, what does too many loci mean? So there's a threshold for how many locations that a read can map to before STAR will just not say that it can't map. So it just won't map it. So you could set that threshold. I can't remember what the exact option is. We use the default, which I want to say is like 10 or around there. But don't quote me on that. I have to go back and look at it. But yeah, so you could set a threshold in STAR, and it of course has a default to say if it maps to more than this number of locations, like I don't even want to bother with it. It's just too many. Cool. Yeah, so there's a whole bunch of information in here. So I'm just asking you questions on the things that I look at mostly, but if you guys have questions about any of these things, feel free to ask away. Another question I got for you is, were there any splice regions identified? And if so, how many splice regions in total were identified? Thank you, Dr. Heller. So yeah, locus is Latin for place, which means in our context, location on the chromosome. So the plural of locus is loci. Sorry, that's a common term in bioinformatics. Yeah, Diksha, Zaru, Leah, Hannah Lee. All right. So the question was, how many splice regions are identified? And, oh, wait. Some of you guys are right, some of you guys are right. I'm sorry, looking too fast. Yeah, so Zinru, you're right. Diksha, you're right. Aowen, you're right. So Hannah Lee and Leah, you guys, I think we're looking at the number of annotated ones. So let's take a look at this. So it tells you explicitly the number of splices in total that it identified is right there. No problem. And so what we're seeing is that the number of splices that it identified was just over 38 million and a half total number of splice sites it identified. Yeah, no problem. But you're getting ahead, because the next question I have for you guys is, how many of those splice regions were annotated and how many of those splice regions were non-canonical? Yeah, Diksha, that's right. Yeah, now it's the right number, Hanley. Yeah, Evelyn, yeah, right. And so it tells you explicitly the number of splice sites that are annotated right there. So again, the majority of the splice sites that were identified were annotated. And then it kind of breaks down those total number of splice sites. So these splice sites here that are explicitly written out, so this is just regions that are commonly where splice sites occur. So during that alternate splicing or splicing out of the introns, the location between the last place of the exon and the first place of the intron that's being spliced is actually pretty common. And so those are considered canonical splice sites. And so canonical splice sites are ones that are basically most common. And so usually a splice site happens when there's a GT on the last part, the end part of the exon. By end part, I mean the 3' end, because we're always thinking 5' to 3'. So on the 3' end of the exon, and then of the 5' end of that consecutive intron. So that's a common location for a splice site to occur. This is another common location for a splice site to occur, and so is this. However, splice sites can happen in other locations besides just there. And so those are considered non-canonical. So if they're not in these kind of common places that splice sites happen, they're considered non-canonical, which just means not usual or uncommon, if you will. So that was all the questions I had for this log final out file. And the next thing that I want to do, and I'll ask you just a few questions about this, and then we should be able to get into the counts lecture before we head off to break. And so you guys remember using that multi-QC function to compile all of our quality control reports from the FastQC or from the FastQ files? Well, if you remember when I talked about multi-QC, it's a really nifty tool, and it actually compiles outputs of like logs from most any tools that look at a quality or a log file, which just tells you what happens in that tool. And so what we used it for before was to compile all of our FastQC results, which looked at the quality of our sequence data. And so now we're going to use that same tool, except this time we're going to be compiling all of those log final out files for all of our samples. Because so far we took a look at just one, but of course it's often useful to look at all of your samples together just to see how your mapping quality is across all of your samples. So remember, we have 12 samples in this data set, 6 from spaceflight, 6 from ground control. And so this command should look familiar to you now. So we're running that multi-QC function, except this time I'm using that -n flag, which tells you what name you want to put on the prefix of your files. And so this time I'm going to tell it to prefix it with a line multi-QC so that I know that these multi-QC files are generated from our alignment data. And then you tell it where you want to output it. So we're going to output this in our home directories as part of that directory structure that we set up at the beginning of the Jupyter Notebook yesterday. And then a positional argument is to tell it the location of where it can find all of the log files. And so what I did is I grabbed that, because if you remember, star outputs 3 different log files. And so the log final out file is the one that we've been looking at. That one's the most informative. The other ones actually have a lot, well, I should say most informative, easiest to interpret and read. The other 2 log files are really for troubleshooting purposes and are massive and kind of difficult to parse through. So what I did is I just created a folder and I just put all the log final out files in that one folder. And that's the path to that folder is stored in the variable star logs. And so we're just telling the multi-QC to look in that star log folder and to compile all of the log files that are in there. So we can go ahead and run that command. And this standard output should look pretty familiar to you guys, right? So again, multi-QC tells you what version you're using. It also lets you know if there's a newer version of the tool, which there is. It tells you where it's searching for the files that it's compiling. It tells you how many reports it found. So it found 12 reports. Are we expecting that? Yeah, why are we expecting 12? You can unmute your mic or write it in the chat. 12 samples, right. So just a quick question for you to come full circle. If you remember in the FastQC files, when we compiled those, how many reports did we have? 24, yeah. So we had 24 then. Why do we now only have 12? Any guesses? You guys can unmute your mic. Combined forward and reverse, yeah. So, yeah, we're not seeing the forward and reverse read separate, right? So when we do the alignment, we're actually, we tell it as an option in the alignment that this is paired. And so what it does is it considers that forward and reverse of course coming from the same sample. So it's giving us all the alignment file for those mate pairs for each sample. So then we're left with a log file for, and also, you know, BAM file, of course, and all of our outputs, 1 per sample. Right. Okay. Already went over the input. So again, here the input data this time is going to be those log final out files. And then our output data, as we know, coming from multi-QC is going to be a folder containing all of the data that it compiled and an HTML report that's going to show us a nice graph of what those data look like. And so let's take a look at that, and then we'll answer these 2 questions, and then we'll get to talking about counts. So go ahead and run the library for us to be able to view this HTML file in Python. And then we'll run this next code block to go ahead and take a look at that HTML file. Is there anyone who is not able to open the HTML file? Okay, cool. Let's take a look at it. So I just have 2 questions. So again, I always press this just to make sure I'm seeing all my samples, but we do see all 6 samples here, at least on my end. If you don't, make sure you press that arrow, that down arrow, and make sure, sorry, all 12 samples, and make sure you're seeing all 12 samples. Again, 6 from your spaceflight mice and 6 from your ground control mice. And so you'll notice that this multi-QC report, it's a little bit shorter, it's a lot shorter because the information that it's compiling is less than the FastQC. And so what we see here is, again, coming from that log file, is it gives us the total number in millions of reads that were aligned. And then it also gives us that number in percentages. And it shows us this in two different ways, right? So we have the percentages written out and we have the number of reads there, and then it also graphs it for us as well and tells us information about the mapping. And so let's first look at this, and then all of mine are based on the other one. Okay, so yeah, it's total percent aligned, and this is the raw number of reads that were aligned. So this is percent of total reads for each sample. And I like to take a look at this just to see, you really want to see, especially for well annotated genomes, like the mouse genome is really well annotated. You should see the majority of these aligned. And so really, for well annotated genes, I really want to see around 70% or more aligned, ideally. I'll be okay if it's around 65. It's not great. If it's below 50%, then I'm like, oh, something went wrong, or there's like a big contamination in one of these samples or something like that. So I'd be pretty happy. I'm pretty happy seeing this percent alignment for each sample because they're all well over 70% of the total reads. And then this here is a really nice graph because it breaks down the number of uniquely mapped reads, reads that mapped to multiple location, reads that weren't counted because they mapped to too many locations. Again, that's a setting on STAR that you could put, or you can have the default, or reads that were unmapped because they were too short. So I know we didn't talk about that in the alignment file or in the log file itself, but the log file will also tell you how many reads didn't map because they're too short. So similar to the other tools we've been looking at where we had this cutoff for read length, STAR also has a cutoff that you can set, and we have it for 20 base pairs. So if it's not able to align 20 base pairs of a read to a place on a genome, then it's considered too short. So if it aligns, 18 base pairs, that's not enough for us to be confident that it's going to align there. So it won't align anything unless it's at least 20 base pairs are aligning. And so you could look at this again in the raw numbers, or you can do percent of the total. And so I always like looking at percent of the total, especially when I'm comparing samples, because then we can kind of account for those differences in read numbers. And so taking a look at the percent, I want you guys to look at this information and let me know, what are the min and max percent uniquely aligned reads for all samples? And so what you could do here, as you notice, is if you hover over each sample, you can see the exact values, and it's given the raw number is on the left, and then the percentage is in parentheses on the right. So I want you guys to kind of take a look at the percent uniquely mapped reads for each one of these samples and tell me which sample has the lowest percent and which sample has the highest percent of reads that were mapped. And you can kind of get a guess because, again, we have all these percentages here. Actually looking at the total, I think, helps too, the raw number of reads. So you could look at it in the raw number of reads, it'll give you the same information, or in the percentages. So I'm looking for the sample that has the fewest percent uniquely mapped reads or uniquely aligned reads, and I'm looking for the sample that has the most percent uniquely aligned reads. So once you guys have that answer, go ahead and put it in the chat. Flight Rep 3 has the most I'm seeing. Yes, that's right. Ground Control Rep 6 has the least. Yes. And what's the range that we see here? I see some of you guys put the percentages. I like that. Kyle did. A couple other you guys did. So yeah, so we're seeing that the least percent mapped reads sample has 75.9% of their total mapped, and the highest has 80.2% mapped. So how you guys feeling about that spread of the percent of reads mapped across samples? You think that looks good? You think that it should be tighter? You think that, what are you guys thinking about that? Yeah, smaller spread is always going to be better, but 4 to 5% handily, yeah, I think that's pretty good too. So yeah. So these are all pretty close to the percent of total that were mapped. So that's nice. That tells me that's pretty consistent data, which is nice. It's around 70% mapped considered passable. Yeah, so Ivana, if it's a well annotated genome, yes. So a mouse genome is well annotated. There are some genomes that have, if you guys remember me going over those FASTA files and looking at the, let's look at it. Here we go. Okay, so this is looking at the FASTA file of a genome build. And so this genome build, if there's like a gap in the assembly, so if we don't know or aren't sure of what the bases are in a certain location, they'll have ends. If we're not confident, sometimes they're represented by lower cases, but that can also be just repetitive regions that are kind of masked. And so some genomes are not well annotated, meaning, so not just with the FASTA file, but also looking at the number of locations on that FASTA file that have annotations. So in addition to looking at the FASTA file, you also want to consider how many locations are known and either have a known function or at least know that this region represents a gene or represents a transcript or an exon or an intron. That's what I mean by well annotated. And so the mouse genome is very well annotated. So the build is pretty close to complete. It's over 95% complete. Same with the human. And it's pretty well annotated, so we know what a lot of the locations are on there. However, for some of you guys working with lesser used model organisms, so I did my postdoc with Xenopus, and those are frogs, African clawed frogs. They're awesome, but their genomes are not well annotated. And so I actually did the first RNA-seq project I ever did when I was a postdoc, and the data was so confusing, the mapping wasn't great. It was like all around 40-50%. And it turns out that that's how I learned that if you don't have a genome that's well annotated, your mapping isn't going to be great because you're just not going to be able to identify the location of where things come from because it's just unknown for that organism. Yeah, so there's no really hard, fast, and rule threshold. So if you ask 10 different bioinformaticists what they would consider as good percent alignment, you'll get 10 different answers. But I think most of them would consider for a well annotated reference that if you have over 70%, that's a good mapping. Good question. Okay, so I just have one more question here, and then we might get started on the counting. So what are the min and max percent of aligned reads that map to multiple locations? So again, I want you guys to kind of hover over and find the sample that has the lowest percent of reads mapped to multiple location and the sample that has the highest percent of reads mapped to multiple locations. Rep 3 and 4, 13% max. Diksha, yes, that is right. So there's a tie for ground control rep 3 and ground control rep 4. They both have the same percentage at 13%. Which sample has the lowest percent of multi-mapped reads? Flight rep 3. Oh, you got one a little bit lower than that. That's close, Christina. So flight rep 2 is 11.1%. Flight rep 3 is actually 11%, 11.0%. So very close. Yeah, so again, we're seeing a nice tight spread of the multi-map locations. However, we're still seeing for all samples have at least 11% or more of their reads are multi-mapped. That's quite a bit, right? Like 1 in 10 reads are multi-mapped. So are we going to throw that much information away? Like, what are we going to do with those? Let's find out. Before I move on, any other questions about what we've done so far on the Jupyter Notebook? Okay, cool. Let's take a break and from the notebook and let's talk about how we start counting this stuff. So I'm gonna turn off my video for the lecture part. Okay, so we have aligned reads, now what? There's a lot of information that can be derived from RNA-seq alignment data. Of course, differential gene expression, which is what we are going to be generating. However, in order to do that, we need to count our aligned reads, which is what we're going to be talking about now. But there are more things that you could do than just that. So depending on how you prepared your library, because we prepared it with ribodepletion, well, this you can do with ribodepletion or poly A, is identify novel transcripts. And so, and this is telling you can also identify different splice isoforms if you do that to pass alignment, which is what we did. You can identify splice isoforms, and you can also quantitate them, but of course that is only if you use a splice-aware aligner. So if aligners know and can recognize splice isoforms like STAR can, you can identify splice isoforms, and then because of that 2-pass, again, we can also quantitate novel ones. You can perform variant calls. So this is looking at differences between samples or differences between the sample and the reference genome. So you can look at single nucleotide polymorphisms, which I showed you what those are. So just little single base pair changes, again, between your samples or also your samples relative to your reference. You can also find insertions or deletions, commonly referred to as indels. You can also, if you use your ribodepletion method, you can also identify and quantitate all sorts of RNAs. So just a couple here, long non-coding RNAs, pseudogenes, small RNAs. There's a variety of different types of small RNAs. So microRNAs are probably ones you guys are most familiar with. Also small nuclear RNAs, there's Pee-wee RNAs, there's snow RNAs, a whole bunch of RNAs. There's people that love RNAs say that it's a transcriptome world. I don't know how much I agree with that, but anyways, so we can do a whole bunch of stuff with those alignment BAM files. However, what we're going to do is we're going to quantify it because we want to do differential gene expression. And so just to kind of remind you guys of where we are in our pipeline here. So we have done our quality raw read check. We've trimmed our data, checked the quality of our trimmed data. We have aligned our data and took a look at how well our reads aligned. And so we are now ready to quantitate. And so let's get into it. We use a program called RSEM to do that. Let's talk about how we count these first, though. So to determine the expression level of each gene in every sample, we're going to have to assign or count the aligned reads, of course. So there are, like every step in this pipeline, there are several tools available to quantitate gene expression data. And some of them are also aligners and just kind of have embedded within them the ability to do counting. So STAR is actually one of them. You can generate count data with STAR by adding another option. And so the different types of quantitation tools use different algorithms to do the quantitation. And I kind of broke them up into two different groups, weighted and non-weighted, to do the quantitation. And I'll get into what that is in a minute. So some of the main differences between the quantification tools are how they handle those multi-mapped reads, and also reads mapped to multiple, reads mapped to multiple genes or splice isoforms. As we saw, we absolutely have them. And so just to kind of remind you guys in a pictorial representation of what multi-mapped reads are. So this is looking at reads mapping to different genes. So we have a read here in purple. I have gene A here in green, GB in blue. And so we have this read in purple, right? And it maps to this region at the end of gene A. And it also maps to this region at the end of gene B. So should we assign that read to gene A or gene B? Looking at different splice isoforms. So just to remind you guys, this is pre-mRNA that we're looking at. I defined what all the colors mean here on the right, but we have our 5' and 3' untranslated regions, and then I have the exons indicated in red and also numbered, and I have the introns indicated in this bluish gray color. And so what you can see is from one gene, we can get multiple splice isoforms, right? So here we have isoform A, which contains all 6 exons of this gene, and isoform B here contains 5 of the 6 exons. So it's missing exon 3, right? So if we have a read, again in purple, and this read is aligning to the junction between exons 1 and 2, well, exons 1 and 2 are in isoform A, and exons 1 and 2 are also in isoform B. So again, did this purple read come from isoform A, or did it come from isoform B? So again, there's two different ways to quantitate these reads. And so weighted and non-weighted, specifically these multi-mapped reads. And so non-weighted quantitation tools If it has a read that overlaps a read is counted if it overlaps one or more gene. Multi-mapped reads will either not be quantitated for non-weighted tools, or they'll be quantitated and it'll be assigned based on the tool option that you select. And so this generates gene quantitation and raw counts, these non-weighted quantitation tools. And then I have some examples here. So HT-seq count, this is a type of non-weighted quantitation tool. And this actually has options that you can select for how you want to handle your multi-mapped reads. But the options are pretty restrictive. So you can have none, you can have all, you can have fraction, or you can have random. So if you select none, that means that if you have a read that's mapped to multiple locations, it just won't count that read. It'll throw it away. If you select the option all, then that means that if that read maps to multiple locations, then you will count it as one mapped read for every single location that it maps to. If you choose fraction, it'll divide a one full count based on the number of places that it maps to. So if you have a read that maps to 2 locations, what this option of HT-seq count will do is it'll say, okay, this read maps to 2 locations, so we're going to say that 0.5% maps to location 1 and 0.5% maps to location 2. So this is starting to get into how we have fractions when we're counting our reads, which feels like that was a question you had on day 2. The other option the HT-seq count provides is a random option. Oh, and I should say that this fraction option, it'll split it up equally among the number of locations that it maps to. So if we have a read that maps to 3 different locations, it'll each be assigned 0.33 counts. And then the other option for HT-seq count is random. And so that means that every time it comes across a read that maps to multiple locations on the gene, it'll randomly pick which gene to assign that read to. And so another non-weighted quantitation tool is feature counts. And it only has 2 options for multi-mapped read. Either you don't count any of them, or you count +1 in every single location that it maps to. Star actually also can generate count data. So there's an option in Star that you can select, and it'll also generate a count value for you for each one of your samples for each gene. And what Star uses to do its quantitation is it uses the default of HT-seq count. And the default of HT-seq count is none. And so this is one of the reasons that we don't use Star to do our quantitation. And this is actually a point of contingency in our AWGs when we were trying to select our quantitation tool. And so, yeah, we ended up not going with Star because of this limitation, because we didn't want to throw away all reads that are multi-mapped. And so in addition to these non-weighted quantitation tools, we also have weighted quantitation tools. And so weighted quantitation tools utilizes the maximum likelihood estimation method to assign reads to genes or transcripts. Examples include the Salmon and Callisto. So this is that mapping that uses the K-mer base. So it looks for patterns in the transcripts and patterns in the read, and it assigns reads to transcripts relative to the patterns that it has. Well, it does that quantitation by calculating the maximum likelihood that that read is belongs to that transcript. And it generates its counts in TPM, which is transcript per million. And we'll get into what that means a little later. And here's links to both Salmon and Callisto if you want to read more about how they do it. The tool that we select, which is a weighted quantitation tool, is RNA-seq by expectation maximization, more commonly referred to as RSEM. And so RSEM will quantitate uniquely aligned reads. And then after it quantitates the uniquely aligned reads, it uses the maximum likelihood abundance estimate to assign multi-mapped reads, taking into account where those uniquely mapped reads aligns. And it will actually give you count data in 3 different formats. It'll give you count data as raw counts, well, weighted raw counts based on the maximum likelihood estimation. It'll also give you count data in transcripts per million and fragments per kilobase per million. And we'll talk about what all of those mean after the break. So we are officially at 10:40, and this is our scheduled break. And so I will let all you guys take your break for 20 minutes and just be back here by 11 and we'll pick up where we left off.